Hello everybody, this is Mr. Steele. I'm going to be working through the next video in the Let's Calc series. In this one we're going to be working through the final problem set from the third unit, which focuses on analysis using derivative graphs. So the title of the lecture and lesson is Analysis with F', and we're going to be actually looking at how you can use that analysis, as well as your understanding of concavity, increasing, decreasing, maxima, minima, points of inflection, all that good stuff, to analyze a function we don't see, using only the graph of its derivative, which we do, or even possibly its second derivative. So in this video, I'm going to go through a bunch of examples. I'm going to do the first one, which is really basic, just like literally looking at a derivative graph and naming what's there. I'm going to also justify, even though you don't have to on that assignment. And then second, I'm going to look at the big problem that is kind of authentic, has a bunch of really good, rich questions in it, and a little bit of the third, and then we're going to call it a day. So this one could move pretty fast, but there's going to be a lot of information, and especially if you walked out of the lecture thinking, geez, I really don't get that, this might be a good place for you to start your attention and start working through things. So without further ado, let's jump right in. Okay, the first problem, as I said, that we're going to look at is problem number 1. And problem number 1 asks you to find basically a smorgasbord of stuff, all involving what you can find on a function f. But of course, you're given the function derivative, f prime of x. So to start off with here, in the instructions for number 1, it says consider the function f of x, and you're like, okay, cool, but where is it? Well, we don't see f of x at all. It says the graph of its derivative, f prime of x, is shown at right. So that means this graph over here represents and is plotted the slope of f of x. And now that's not going to help us with specific values. It's not like we can say that the slope right here is 3 because there's no vertical labeling. But what we can say for sure is that the slope is 0 at particular points right there. And it can also tell us about the sign of the slope, as well as whether the slope is increasing or decreasing. That is the theory behind looking at a graph of f prime. F prime tells us a bunch of information about the slope, or the rate of change of our function, and all we have to do is read that out and translate it appropriately. So we want to find a whole bunch of information for what's there. My goal here is to use a whole bunch of different colors and like color the graph all up on this first one, just so you can really see and really clearly see from side to side. So let's do it. What do we got first? So first, for 1a, it says find the x-coordinate of all relative maxima. So we know that relative maxima look like this. They're places where f itself goes from increasing to decreasing. But remember, we aren't given f. We're given f prime. So we need to use the definition of f prime, or the definition of a relative maxima using f prime. We know that a function f has a derivative at a point x equals c when f prime changes from positive to negative. Because in a sense, that's really what increasing means. F prime is positive, then it tops off, hits a place where it's 0 for a second, and then it starts decreasing, meaning that f prime would be negative. So in our example, what we're looking for is exactly this. We want to find where f prime changes from positive to negative. So looking at our picture, all the positive slope is up here, above the x-axis, and all the negative slope is down here below the x-axis. So we're looking for places where this slope graph explicitly changes from positive to negative. I see one spot right there, because our slope was positive up here and negative down here. I see a second one right there, where once again our slope was positive above and negative below. So for us, there's going to be 2. Those 2 coordinates are going to be at x equals, it looks like negative 1, 2, 3, 4. So there's a relative maximum at negative 4, and there's going to be a relative maximum at 1, 2, 3, 4, 5. And although, again, it did not ask us to justify if we wanted to, we could say that the reason is because f prime changes from positive to negative. So there are the 2 relative maxima that we'd have for this particular function. So next, what we're looking for, I'm guessing it's probably minima. Is it minima? It is minima. So the x-coordinate of all relative minima for f of x. So for relative minima, again, we know what those look like. Relative minima are those. They're places where f, the function itself, changes from decreasing to increasing. And again, that should make sense for a minimum, right? If you're decreasing for a while and then you stop decreasing, you've decreased the most you're going to decrease, then you'll start increasing again. So that's literally the creation of a minimum. Once again, though, the tool that we're provided is f prime of x. So we're not going to be talking about f changing from decreasing to increasing. we're going to talk about f prime changing from negative f prime, which would mean f is decreasing, to positive f prime. So we want to go this time from negative slope to positive slope, because right down the middle, negative slope on the left, positive slope on the right. So looking up here, we're looking at the zeros again. There's definitely one right there. So that's going to be at -6. So I'll even write that down just to save us a little bit of time. And then I believe there's one more. There is. Right there at x equals 1. So there are two relative minima. And again, you can see from the slope, we're going from negative slope down here to positive slope right there. We've got both of those pieces in place. And again, our rationale, if you wanted to write one in there, would be because f prime changes from minus to plus, negative to positive there. Voila. Okay, third, we're going to pull up and start to look at points of inflection. Points of inflection, a little bit harder to see. Like if we try to picture what a point of inflection would look like, it'd be a place where f changes concavity. That's definitely true. So the concavity changes. Could be from concave up to concave down, could be from concave down to concave up, like the picture I drew right over here. Fortunately, that doesn't help us either, because we're looking at a graph of f prime. So other things, what else do we know about concavity? Well, points of inflections occur when the second derivative changes signs. So the second derivative might go from negative to positive, or positive to negative. So that's helpful, except not helpful enough in our particular case, because once again, we have f prime. So our question really is, what is f prime doing when f double prime changes signs and when f changes concavity? Well, in our case, f prime is changing as well. Obviously, it's changing. All these things describe some sort of change. F prime is changing. And I'm going to say here, instead of from, I'm going to say between. Yep, can't spell between. Between. Between increasing and decreasing. And what I mean by changing between is that it doesn't matter which one you go from. If you go from increasing to decreasing, if in f prime, you'll have a point of inflection on f. And if you go from decreasing to increasing f prime, you'll also have a point of inflection on f. So in looking at our picture, I see a couple spots. I see one right there. It looks like there's going to be one at x equals -5. I see a second one right here. Appears to be at x equals -2. And then third, I see one right here at 1, 2, 3. I see a third point of inflection. Now, some people would point out and say most obviously, like, oh, it's the relative extrema of the first derivative. And that's true. The relative extrema occur on the first derivative when the first derivative changes from increasing to decreasing or decreasing to increasing. So it should make sense that way. But again, if you're looking for the most formal one, we should be referencing the derivative tool that we have. So I'd say that it's at those 3 points because f prime changes. I could say between increasing and decreasing, like I said on the right side here. Or I could say that it's because f prime changes from increasing to decreasing, or decreasing to increasing. And if you prefer to see a lot of people say increasing to decreasing or vice versa, that's fine as well. In any event, there's all the nice stuff that we were looking for. We've got all the specific points we were looking for. And again, we still haven't seen f, not even once. What we have done is we have looked at its derivative and used that information about the slope to draw some conclusions. Okay, next, we're looking at 1D. So let's keep changing our colors here. So for 1D, we want the interval or intervals for which f is strictly increasing. And notice for D, we have strictly increasing included. So in this case, I'm going to actually do something that's really common when I'm doing some of these problems. So I want to kind of postpone my thinking till a little bit later and just kind of get myself ready, or I just want to get the justifying out of the way so I don't forget it. I can point out that f would be decreasing, like the reason, or sorry, a reason we could give for which f is strictly increasing would be because f prime of x is greater than 0. So in other words, what we're looking for here, for thinking about it, if we want f to be strictly increasing, that's the same thing as saying that we need to find where f prime is positive. So we're looking for the positive areas of the slope graph. So it's weird to think about, because when you look at this section, your mind naturally says decreasing. Remember, this is a graph of the slope. So everything above here is positive slope, or corresponds to f having positive slope. So in here, we're going to have f prime positive right there. I believe that's from, let's see, -6 to -4. What else we got? Oh, we also got it right here. So it looks like it's from 1 to 5. And our reason already provided is because f prime is positive. And again, since this is strictly, we're using strictly less than and strictly greater than symbols. Actually, they're all less than symbols, as it turns out. And again, if it wasn't strictly, things would be a little different. And speaking of being not strictly, we've got, oh, I already used that color. We've got a situation where things are not strictly decreasing in part 1e. They want to know the intervals for which f is decreasing. So following that same strategy as before, I'm going to start by pointing out that in order for f to be just decreasing, that means we want, of course, f prime to be negative, but it could also be 0. We'll also accept 0 when we're doing just plain decreasing. So because f prime of x is less than or equal to 0. So that is the difference here. So in looking, obviously, we've got some nice spots. We've got this spot right there. We got this spot to right here. Coloring it's actually kind of fun to color this way. All the way down to there. And then also, we've got the dots themselves. So a little bit weird to include them. It's always felt weird to me, but that's the difference between strictly and just plain old decreasing. Decreasing allows for that zeroness to set in. So as far as our places where this is true, it looks like we've got x values less than -6. We have x values between -4 and 1. We'll deal with the sign, the or equal to's in just a second. I'm not forgetting about them. Then we've got, looks like 1, 2, 3, 4, 5. Then we also have x values greater than 5. So as of right now, what I wrote here would be for strictly decreasing, but we've got to include all these zeros, which means or equal to symbols will populate all of our intervals. And with that, we've now taken into account where the graph of f, wherever it is, which we haven't seen yet, would be decreasing. And that includes those 0 derivative spots, where it's kind of topped out or stopped changing. So there are 1 D and E. Okay, that brings us to the last section of question 1, which introduces us to the concept of concavity again. So we're in here first interested in f being concave up. So we've got to think about what that means in a bunch of different spots. Now we traditionally know concave up as f double prime is positive. And that's fair, that's good, that's how we learned it probably the first time. And we also know visually speaking concave up, it means that it's opening upward. Like we've got all that good stuff. But the tool we're provided is f prime. So as of right now, talking about f and f double prime, things we don't have, is a little bit like giving you a hammer and then saying the way that you're going to get this screw into the wall is with a power drill. If you don't have that handy, it's not going to really help you work your way through. So instead we need to think about what does this all mean about f prime. And specifically, if f is concave up or f double prime is positive, that's the same thing as saying the slope of f prime is positive, which would be code for f prime being increasing. So when I go to do my work over here, I'm going to say that the reason is because f prime of x is increasing. And that's good, because with a graph of f prime, we can clearly see, visually speaking, where the function is increasing. So in looking over here at our slope graph, we want to know where the function is increasing. So right there, right there. So and in here, this is an interesting one. With concavity, we typically talk about strictly increasing. So even though our definition says because f prime is increasing, we treat it as strictly increasing. Although those or equal to's I would not penalize you for. Looking at our picture though, it looks like our values are x less than -5 and is that -2? Yep. -2 less than x less than 3. So it turns out there are two intervals where f prime is increasing, which means we have two intervals for which the graph of f, which we still haven't seen, would be concave up. Likewise, I'll do one more here. I'll go brown. I actually had a student in my class in, I want to say 2016, who was obsessed with the color brown. His name was Adrian. Fun guy. So from here, we want to know the intervals where f is concave down. Well, you can probably predict that there's nothing really fancy here. It's going to be completely analogous to our previous work. Our reason is going to be because f prime of x is not increasing this time, but is decreasing. We're interested in where this function, slope, is decreasing. It's one of the interpretations of concavity. So looking up there, our intervals, going to have one go right there. In fact, that one is going to be, it looks like, from -5 less than x less than -2. And then our second one is right over here. That one starts at, I think, 3. So, and x greater than 3. So with that said, we've now seen exactly how we can determine where a function f is concave down or concave up using its derivative graph. And again, all these different things, like hopefully what you're starting to realize is that what's most important with all these pieces is knowing the definition and definitions of all of these terms and properties a function might have. And the reason I say that is because knowing the definition is half the battle. If you know that concave up means f prime is increasing, then all you have to do is know how to translate increasing into a picture. You just have to look at a picture. If you don't know the definitions, it's going to be really hard to access. I can't lie. So it's really important at this point, if you haven't already, to start committing to memory all of those definitions, or better yet, just understanding what they all mean and being able to recall them. So you will be expected to do this on the AP exam, as well as, of course, on the test for this unit. Okay, with that in place, that brings us next to question number 2. Question number 2 is, I'd say, a richer question than the first one, where you didn't even technically have to justify. I just kind of did that as an extra explanation. In number 2, you're asked more authentic kinds of questions, the kinds that you'll see pop up here and there in different places on an AP free response question or on a multiple choice question possibly too. So in each of these, we're going to be referencing a graph that's provided for you once more. So no calculator question for sure. It says consider the function h of x. The graph of its derivative h prime is below. We see it. Use the graph to answer the questions. So in looking here in question number 2a, the first thing we're asking is h of x increasing or decreasing at x equals 7. So, and to explain our reasoning. So we need to figure out, first of all, since we don't know anything about h except its derivative, and what we see here, we need to figure out first where is 7. What's the graph of h prime doing over there? So 1, 2, 3, 4, 5, 6, 7. So if that's 7, this is our point that we're interested in. So we're interested in what's happening on h at that spot. There's a lot of things you could use to describe that, but the most important thing here is we're asking about increasing or decreasing, which is just basically talking about the sign, S-I-G-N, of the derivative. We're interested in whether the derivative is positive or negative. Well, since this graph is the derivative, we're above the x-axis, and that means that for us, h prime of 7 is clearly positive. In fact, I'm not even going to write greater than e0. h prime of 7 is positive. That tells us all that we need to know. H prime of 7 is positive, so h must be increasing at x equals 7. So in here to state that, could state it properly by saying h is increasing. And again, there's lots of little things here, so I wouldn't skip all of the writing here. I think it's important to see what's here and why. So h is increasing. Right now, what we've written is a false statement. This function h is not increasing everywhere. Specifically, h is increasing at x equals 7. That way we're focused on the point we are at. Now we need to give our reason, or explain our reasoning. And that reason, as we said, is because specifically h prime of 7 is greater than 0. And you could say, of course, or equal to 0, but of course we know the slope is positive from looking at the picture, so we're done. There is our work, there's our explanation, but note again the presence of at x equals 7. Also note that I didn't put h prime of x is greater than 0. I put h prime of 7, it's just as precise and to the point as we can possibly make it. There is 2a. Okay, next this brings us to 2b. Find the x value of each local maximum of h of x. Now, this is one of those situations where it's a little bit harder to just look at the picture and just pull it out there when you're first starting out. So I think it's a helpful opportunity to jump in and think about what it means to have a local maximum of h of x. And again, we're using the definitions. Like, what does it mean to have a local maximum given h prime? So thinking here, our explanation is going to be because something happens in the slope to tell us that we have a local maximum. And we said it earlier today. It's going to be because h prime of x is changing, and specifically it's going to be because h prime of x changes from, and for a maximum, remember we've done this before, f goes increasing to decreasing, and specifically f prime goes positive to negative. So from positive to negative. So we're looking for where on our graph h prime is changing from positive to negative. There's 1, there's 2, and of course we have to count them. So we're going to have 1 at x equals -5. We're going to have 1 at x equals 8. So it turns out there are going to be 2 relative maximums, 2 places where f starts increasing and then decreases. We found the 2 locations. But again, using information about h prime. Okay, question 2c. Does h have a point of inflection at x equals -3? Well, that's awfully suggestive. So explain your reasoning. So let's see, let's organize here and figure out where h -3 is. Okay, so I'm going to assume this is at -3 right down here. So down there at -3, it looks like the graph of h prime changes from decreasing to increasing. And if h prime is changing from decreasing to increasing, that means the second derivative is changing from negative to positive. So in fact, the answer to this question is yes. I'll make it exciting. Yes. And our reason would be because, and again, using the tool that's provided to us, that's h prime, it's because h prime of x changes. And in this case, we're only looking at one single point, so we can say h prime of x changes from decreasing to increasing. The only time I use between is if we're talking about many different points of inflection. That way we cover all possibilities. Decreasing to increasing. And I could say there, but since I haven't mentioned x equals -3 yet, I'm going to say at x equals -3. And so there is our point of inflection justification. Notice there are other points of inflection on here. I see a point of inflection at 1, I see another one at like 4, like they're all over the place. Excuse me. But for us, we were only questioned about x equals -3, so don't say too much. Say just right. Okay, next that brings us to question 2D, a very common question to answer as well. It asks us, does h have a max, min, or neither at x equals 1? So in this case, we've got x equals 1 right there. And now you can kind of see how you get baited on this question when you're first starting out here, and how easy it is to conceptually mess up. If we look at the picture at 1, you might want to say, oh look, it's a maximum. No, it's the maximum, look, it's a high point. Unfortunately, that would be true if this was a graph of not h prime, but h. But we're looking at h prime. You might also be fooled because h prime equals 0, which can kind of mess with people as well. But here, what's important is the sign change. Notice on the left side we have h prime negative, and on the right side of the value we have h prime negative again. In order to get a relative maximum or relative minimum, we need the sign to change. Because of course you get a maximum when you're going from positive slope to negative slope, or negative slope to positive slope. At our particular picture, we have negative slope, then we have more negative slope. So we don't get a maximum here, we just get what ends up being a point of inflection. So in our answer here, we have to note that this is neither. This isn't going to be a max or min because there's no sign change. So h has neither. I could also say neither. Sounds kind of cool actually. H has neither a max nor a min at x equals 1. And our reason is because of that missing sign change. Because h prime of x does not change signs. Voila. So and again, that's an easy one to look out for, but again, if you just kind of get into your mind that we need a sign change in the derivative for a max or a min, that will take care of you when these things pop up in the future. Okay, 2e. I think this is where we start to get a little bit spicier here. So in 2e, find the open interval or intervals on which h is both strictly increasing and concave down, and explain our reasoning. So there's a couple different ways to approach this, and I've seen students use both approaches in the past. Some students will first identify where h is strictly increasing. So their approach might be to do this. They look at our graph, they say, well, if h is strictly increasing, that's going to mean that h prime is positive. And looking at the graph, we'd see positive right there and positive right there. So we'd be say strictly increasing for x less than -5, and also 1, 2, 3, 4, 5, 6 less than x less than 8. So that would be their first move. Their second move would then be to look at the second property and to say, well, if we want to talk about concave down, we're going to have h be concave down when h prime of x, the tool that we have, is decreasing. Then from there you'd look at the picture and figure out where h prime of x is decreasing. So I'll do it this way. Decreasing, decreasing, and decreasing. So in here we'd have to say that it looks like x is less than -3, 1 less than x less than 4, and then the other one it looks like 4, 5, 6, 7, x greater than 7. So that's good stuff, that's a good start. But our problem here is that we haven't really identified what we were asked for. We want to find the intervals in which both of these things are happening. So what we're looking for is really overlap. Where do these regions overlap? Now the nice thing about using colors, we can clearly see on our picture where that overlap occurs. You can see that happens right there and also right there. So in this case we'd say that both, and I'm just going to shorten the process here a little bit and just say both properties. That's going to be on the two intervals. One's going to be x less than -5, and the other one is going to be, I say 1, 2, 3, 4, 5, 6, 7. So 7 less than x less than 8. So we'd have both properties right there. So this is a perfectly valid way to do it. You get your answer, everything goes out pretty nicely. The downside is, of course, this takes a little while, and sometimes too you may not have multiple colors handy, or you might not have a computer that very clearly lets you see both textures that I marked the graph with. So instead what I usually do is I usually start these kinds of problems backwards, and I start with what the justification would be. So I start with the because, and in our case I'd say because h prime of x is both, and then I'd list out what it takes for each of those properties. So in this case, like I'll just pick colors intentionally, for h to be strictly increasing, we'd say h prime is both positive there we go, and second we wanted to talk about concave down, and concave down happens when h prime is decreasing. So because h prime is both positive and decreasing. So with that justification ready, what I can do is I can then just go find the section of the graph that has what we're looking for. And I'd see the exact regions that we described earlier. We'd see that it occurs when x is less than -5 and x is between 7 and 8. So no matter how you approach it, as I said, this is probably the way I do it normally, but it doesn't really matter how you approach it. What matters is that you can recognize these properties in the graph of h prime and what they describe about this graph h that we're not seeing. We're just kind of deducing information from some other source for it. Okay, question F, or 2F. This is an old favorite question that I started putting on the test, I think back in 2016 in fact. And it's actually really simple, but it's easy to mess up when you look at the picture like this. So in 2F, you are asked which value is greater, h of 3 or h of 5. And what most people do, in my experience, is they go look at the picture and they go, oh, I don't know, man. They look kind of the same. Just like sad face. Worried. Worried face. Yeah, exactly. But here's the thing. It doesn't really matter where those points actually fall. What's important is to look at our graph. So look at h prime of x. So we're interested in this interval from -3 to 5. Well, take into account this interval. What is that, from 1 to 6? So consider this. For all the x values between 1 and 6, h prime of x is what? So looking at our picture, that describes all the x values down here. Oh, and I said down. That's because for all those values between 1 and 6, h prime of x is negative. When h prime of x is less than 0, aka negative, what does that tell us about h? Well, it says h is decreasing. And that's really helpful, because if h is decreasing on the interval from 1 to 6, then that means that any value with the larger x value is going to be smaller than the previous one. That's just what decreasing means. So from us, what that tells us is that h of 3 has to be greater than h of 5. Because of course, decreasing in h, like just picture what h might look like. If we look at something decreasing, for picturing what h could be, we'd have it decreasing, 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 decreasing. So wherever 3 is up here, 5 would be somewhere down here. So out of the two, we were asked which value is greater, h of 3 or h of 5. Our answer would be h of 3, and our reasoning would be to cite what our properties tell us about h from h prime. So we'd say h of 3, and it's because h prime of x is less than 0 for, and we don't have to say 1 to 6 anymore, we can say literally just from 3 to 5. So h is decreasing there. And of course, the classical definition of decreasing without using calculus has to do with f of b is less than f of a for b greater than a. So we actually get to use that definition right here. Okay, next, that brings us to 2G, the final question from this section. And this is a tough question to think about, but I think it's actually very simple once you get your mind around what's here. It's very similar to the last question, in fact. So for 2G, on the interval -5 to 6, what are the x-coordinates of the absolute maximum and absolute minimum of h of x respectively? Can this be determined? Explain your reasoning. So we're trying to work our way through and figure out what's actually going on in this particular problem as far as absolute extrema are concerned. So once again, my focus is going to be to begin with what's actually happening on that interval, -5 to 6. So it's basically us asking, well, what's going on there? Well, here's -5, and here is 6. So what do you notice about the graph of h prime down there? Look at all these values. Would you agree h prime of x is less than or equal to 0 the entire way? Again, very familiar sound here. So if h prime of x is less than or equal to 0 for that entire region, that means, thusly, that h of x is decreasing. And it's decreasing for all x values between -5 and 6. So just like before, where decreasing allowed us to see that one value is smaller than the other, we now know that wherever our graph starts at -5, h is decreasing the entire way. Even with the one little flat spot, it's decreasing the entire way. So putting that into our mind, what that shows us is that on this closed interval, the absolute max, or the global maximum, has to occur at x equals -5, the left endpoint. Because wherever you start, if the function decreases everywhere afterwards, it's just going to keep going down further and further. Likewise, the absolute minimum has to be at the right endpoint, which is going to be x equals 6, for exactly that reason. It's decreased the entire way, so the smallest value it ever gets to is 6, because that's the point at which it would stop decreasing. So with that said, kind of a weird question. It's a little bit hard to explain your reasoning, but once again, that comes from this information, that work that we did up there. Think about what the implications are based on our derivative graph, and then work your way through from there. Okay, that next brings us to question number 3. Now, I'm not going to focus on parts A, B, and C of question number 3 because there's nothing really new in those questions. The only difference is instead of providing you a picture myself, I've asked you to use your graphing calculator to produce the picture of the graph and then analyze the derivative analyze the function using the derivative in the exact same way we did in questions 1 and 2, which I've done the entirety for. So I'm omitting A, B, and C, which are straightforward applications from there. You're doing the same stuff you already have. Instead, I wanted to look at questions D and E, which were somewhat new and really had that AP feel, that AP free response feel, the kind of question that might be tacked onto a problem you're working on there. So in this situation, we're told to first consider a function g whose derivative is given by g prime equals complicated stuff on the interval from 0 to 7. So we're looking at a pretty complex derivative function. We don't know anything about g, at least not right now. But what we do know is that this is a calculator active question, meaning that we're going to need to use our graphing calculator to access the problem and work through the questions that we're given. So on here, I've already gone to the trouble of punching in y1 equals that derivative. So y1 in our case is going to be g prime of x. And then from here, because we're restricting ourselves to just 0 to 7 for x values, I'm going to change my window from negative 10 to 10 to 0 to 7 in the x direction. And then I don't know what everything else is going to look like here. I'm going to put it as negative 5 to 5, just kind of speculatively. But again, you can just graph it from negative 10 to 10 in the y's, and then we can always adjust it vertically if we need to. So here's what our derivative graph looks like. So you can see that even us zoomed in as much as I did hasn't helped enough. It looks like we go down and then up, but I can't really tell if it's on, above, or even just slightly below the line. So I'm going to actually zoom in way more than I did even before. I'm going to go from negative 2 to 2. Okay, it's better, definitely better. Right there you can see that it goes above the x-axis and then below again and comes back down. So there's our picture that we're looking at. So keep in mind too, if you were having trouble setting up A, B, or C, maybe that was your reason why. You needed to zoom in a little bit more just to see it. So now we got it. So let's look at our question in 3D. In 3D as opposed to 2 dimensions. Haha. So it is known that g of 5 equals 4. Okay, so that's actually a weirdly powerful piece of information. As of this point, we only knew what the derivative was. We didn't have any single point on the original function, but now we have a single point of context. We know that if you plug in 5 to that function g, whose derivative is this guy, that we're going to get 4. So keep that in mind. That's a pretty powerful starting point. From here, next it asks us to write the equation on the tangent line to h of x equals 3g of x squared at x equals 5. So we're actually doing a tangent line problem with a function that uses some information about g as well as the derivative g prime. So it's kind of an interesting place to work. So let's try to consider what we've got here. So let's do some stuff here. So if we want to find a tangent line, we're eventually going to need to figure out the y value. So our y value is going to be h of 5, which is going to be 3 quantity g of 5 squared. So pretty standard stuff right there. And the nice thing is, because they told us g of 5 is 4, this is actually just going to be 3 times 4 squared, which is 3 times 16, or 48. So interestingly enough, the y value is just 48. We didn't have to use the calculator at all, which is kind of a nice thing. Our problem is going to accelerate in difficulty, though, when we consider the slope. So we also need to figure out what h prime of x is equal to, so that we can eventually plug in 5 to get the slope of the tangent line. So h prime of x in our case is going to be the derivative with respect to x of 3g of x squared. So that's telling me that we're going to need to use the chain rule. So although I've promised to not do the full derivation or the full decomposition every single time, I think this is a good time to pull it out. So since h of x equals 3g of x squared, I'm going to let h of u equal 3u squared. I'm going to let u equal g of x, and then I'm going to compute the derivatives of each factor. H prime of u is going to be 6u, u prime is going to be g prime, and if we multiply those pieces together, we're going to get 6u g prime of x. But remember, we said right there, u is g of x. So our derivative here is actually 6g of x times g prime of x. So over here, we can include that right away. This is 6g of x times g prime of x. That gives us our expression for h prime of x. Now we aren't interested in h prime in general, only as a tool to compute h prime of 5, the slope at x equals 5 that will represent the slope of our tangent line. So plugging in 5, we get 6g of 5, g prime of 5. And some of this is easy. G of 5, we've seen that before. That was 4. So in other words, our derivative is going to be equal to 24 g prime of 5. But our difficulty here is we don't actually know what g prime of 5 is. That's where our calculator comes in. So I'm going to take advantage of our calculator. Now you have to be careful here. We want g prime of 5, and in your mind you might be thinking, okay, well we just need to use math aid and find the derivative, or even go to second trace and then do the intersection, or do the dy dx. But that's not true. G prime is y1. y1 is x minus 3 arctangent of x times ln of x plus 2 cosine of x. So in other words, we don't actually need to do anything except plug in 5 to that function. So doing exactly that, we can do, let's see, alpha trace, we'll do y1, and then it'll be of 5. And we'll get that our value for g prime of 5, which we're in their calculator is called y1 of 5, y sub 1 of 5, is going to be 1.510. So 24, 1.510. And of course we know that since this is an intermediate calculation, we want to maintain full decimal accuracy just in case. So I'm going to leave it exactly like that, and then I'm going to find what that's equal to on the calculator. So if we take that answer, we straight up multiply the answer by 24, we get our slope of 36.2528, so 36.253 will be our accurate decimal, will be enough decimal for us to work through. So given that information, we can finally finish off this problem by writing out that the tangent line is y minus y1 equals m. And yeah, we know this isn't the perfect slope, but again, we're constructing a tangent line, so this is all the accuracy we need, times quantity x minus 5. And again, the cool thing here is we don't know at all what g of x looks like. We just know a single point on there and what its derivative looks like. But yet we're still able to construct a tangent line as though we did. Okay, that brings us next to 3e. 3e is still using the same derivative function, but this time it harkens back to the mean value theorem a little bit. In 3e, we're told that the average rate of change of g of x on 1 to 6 is 2.4, and we are supposed to find the value guaranteed by the mean value theorem. So if you'll recall, the mean value theorem from a few days ago, the mean value theorem says if a function f is continuous on the closed interval from a to b, and that same function is differentiable on the open interval a to b, then there exists a c in that open interval. So in other words, there's going to be an x value where the average rate of change, f of b minus f of a over b minus a, is equal to f prime of c. So in other words, we're looking to find the place where this is true, assuming we can apply the mean value theorem. Before we can start that though, it's worth asking, can we even apply the mean value theorem? Because if this is a trick question, that technically makes it go even faster. So in thinking about this, the first question is, do we have continuity and differentiability? Well, even though it's a small thing, from looking at our function, our graph, we can see that the derivative, g prime, looks to be continuous on 0 to 7. So g prime of x is continuous. And we said it was for 0 to 7, but we're interested in 1 to 6. So it's clearly continuous for 1 to 6. That means g is differentiable. Because remember, having a continuous derivative, first derivative, means that your original function is differentiable. And if g is differentiable, because differentiability implies continuity, g is also continuous. So that actually answers all our questions. We've guaranteed that g is differentiable for the full interval, and of course then that means g is also continuous for that full interval. So we've got that the mean value theorem applies. What we want to then figure out then is g of 6 minus g of 1 all over 6 minus 1 is equal to g prime of x. So we're trying to solve that equation. And this is where things can get a little weird. It might feel like there's just not enough information because we don't know enough about g. And the answer is no, we don't. But they told us the average rate of change of g of x on 1 to 6 is 2.4. That means this expression, the difference quotient that represents the average rate of change for g on 1 to 6, is 2.4. So what we're really trying to do is solve the equation 2.4 equals g prime of x. And to solve that, we can pull into our working area, our graphing calculator. We can let the calculator solve that equation using intersection. So let's do that. So we already graphed that. We want to next graph 2.4, because that way we'll have one line graphing h prime, or g prime, excuse me, one line graphing 2.4, the average rate of change. And then specifically here, we're interested in values on 1 to 6. So I'm going to change my x min and x max to 1 to 6. And for my y mins, remember we zoomed in them pretty far? We need to make sure 2.4 is visible, otherwise we can't solve it. So I'll change this so the y values range from 0 to 3. With both those in place, I can graph. Notice that there's not much function down below, but right up there we have a single intersection point. The mean value theorem guarantees there's one there, and we already showed that the mean value theorem guarantees us a value. So I'm going to second trace. We'll find the intersection. I'm going to go enter, enter, and enter. There's only one intersection, and it occurs at 5.424. I'll say approximates. Let me make sure I did that correctly. 42419, yep. So there's our value. So again, what this is telling us is that the place on the graph of g, that function we don't see, but whose derivative is given to us as g prime of x, at x equals approximately 5.424, the slope of the tangent line there will have the same slope as the secant line, which in our case has slope 2.4, because that's the value of the average rate of change. So again, it's a really interesting question. There's a lot of little pieces in here, but there's not really that much that you have to do. You're literally just finding an intersection on a graphing calculator, but look at how involved and interesting the package became to hide that simple intersection question. So this is 3E. It's a pretty good upper level question, I'd say. Okay, so that brings us to the final questions we're going to attack, which are going to focus on question 4A and 4B. And the reason I'm bringing these up isn't because they're particularly difficult, but simply because they're an example of a type of question that we haven't asked or addressed before. So everything up to this point has focused on giving you the graph of f prime or h prime or g prime. In any event, it's always been the first derivative that you've been given to analyze. But in question 4, you're actually provided not the first, but the second derivative. So you're told that k double prime equals this 3 to the cosine of x all minus 1 expression. So we have to analyze a different type of function in a slightly different way. So to just kind of illustrate how those things work a little bit differently, let's first look at what this graph looks like and just get a visual picture in. So as usual, I went to the trouble of plopping this into the graphing calculator. So I've got it in. In fact, I can probably make this a little bigger. So I've got this thing in there. It says y1 equals 3 to the cosine of x minus 1. Now we know that represents k double prime, but it's in there in the calculator. And then second for my window, I'm going to let it go from 0 to 7. And I don't know much else about what this function is going to look like. So I'm going to maybe we could probably think about this. Let's just go from -5 to 5. That usually seems pretty standard, but again, we could go -10 to 10 and be fine too. So let's see what this graph of k double prime of x looks like. Okay, so pretty simple looking graph. Let's copy this really fast. Get this in there. So here is the graph of k double prime that we're going to be analyzing this entire time. And in fact, for the sake of simplicity, I'm going to go place it on the other one really fast too, just so we got it. Okay, so there's k double prime. So the first question asks us for what x values, between 0 and 7 of course, is the graph of k of x concave up, and they want us to justify our answer. So as usual, I'm going to do this first. I'm going to care about the justification before I do anything else. So the question for me is, how do I know that k of x is concave up? Well, we could look at the picture. We could look for k of x. Remember, we've got all these reasons. We've got k concave up would mean that it's opening upward. We could look at k prime and talk about k prime increasing. But in this case, we're given k double prime. So we just need to think about what k double prime needs to be for k to be concave up. And that is obviously positive. So we want a positive value of k double prime. So in other words, in my justification here, I'm going to write first that wherever it is, it's going to be because k double prime of x is positive, or I could say is greater than 0. So in looking at our picture, we want the positive areas. So the positive areas are going to be from right there to the first 0, so we'll need to figure that out. And then from the second 0 on to the endpoint. So in fact, we can even tell some of these values. We're going to have values between 0 and that first 0, which is kind of awkward to say. And then we're also going to have values from the second 0 up to 7, because those are the boundaries of our window itself. So our job, of course, is to use the graphing calculator to find those values. So let's do exactly that. And more importantly, let's make it room so we can actually see what's going on here. I'm moving this higher up. There we go. Okay, so we just need to find some zeros. Not hard at all. Second trace, we want to find the 0. Now for the first 0 over here, I'm going to go between 0 and it looks like 2. And I'll guess 1. And it finds me the 0 of 1.5707. So that's going to give me 1.50. Was it 1.57? It was, wasn't it? 1.5707. So 571. As a heads up, in case you're interested, by the way, that is pi over 2. But we don't have to know why. But we can go with the decimal value, of course. And then our second 0, second trace, 0. I'm going to check this one. I'm going to go from 3 to 7. And I'll guess, I don't know, 6. It says that one's at 4.712. And as a heads up, that is 3 pi over 2, just so you know. So there are our intervals on which the graph of k, whatever that looks like, is concave up. And of course our reasoning was simply that k double prime was positive, it was greater than 0. So in other words, k double prime is positive. So we can tell by looking at the graph of k double prime over here and figure out where is it above the x-axis, because that would imply, right, anything up here and above is k concave up. So there you go. Nothing really crazy. We just had to know what it means to be concave up using the second derivative, since the tool we were provided was the second derivative. Okay, and finally that brings us to the last question we're going to address together in this video solution set. That is 4b. It says find the x-coordinate of all points of inflection for k on 0 to 7, and to justify our answer. So let's think about this a little bit and start to work our way through. So we're going to find all the potential points of inflection on 0 to 7. So looking here, of course, once again, we're thinking about justification. So if we're talking about a point of inflection, of course, we've talked about in the past, like lots of things about like k prime changing between increasing and decreasing. But once again, we're given k double prime this time. So in other words, if we want to talk about points of inflection for k using the second derivative, we'd say because k double prime changes signs. So in other words, k double prime goes from positive to negative or negative to positive. Doesn't matter which one. So looking at our picture, I see one potential spot right there, and I definitely see one up there. And I could see an argument made for 0 to be included, but for our argument here, for our sake, we're not going to worry too much about that one for the second. So we're going to look at the two obvious ones in here. In fact, really, I should just change this question to open interval. So maybe I'll do that. So we're looking for where k double prime changes signs. We found that that's at the relative minimum and the relative maximum. So all we need to do is calculate out and find their x values. So we've played this game before. We're going to start with the minimum. It's the smaller one. We'll go down to 3. Minimum, let's go from 2 to 4. And we'll guess it happens at 3. That happens at 3.14159. Huh. That's an interesting number. 3.142. As a heads up, it's no coincidence. That is pi, by the way. And our other one occurs at that relative maximum that we see. So second trace, we'll go 4 for maximum. We'll go right there to 7. We'll guess, not 3, we'll guess 6. It tells us the maximum is at 6.2831. So 6.283. And I bet you can predict what that value is. Indeed, it's 2 pi. So we found our 2 points of inflection for the original graph of f, which is cool. But again, we were able to work through that because we were given k double prime, and hey, k double prime tells us a ton about points of inflection. Second derivative is the, like, I don't know, the birthplace of points of inflection. And without further ado then, that completes our work on this video solution set. I hope this has been informative. Hopefully this has given you some extra examples or clarified some things or helped you through some of the more difficult questions. But in any event, thank you for watching. This is Mr. Steele signing off for the night. Have a good night.